Suppose I give you three types of data. This one, and I plotted over here. This one, plotted over here. And this one, I'm plotted over here. And I ask you to tell me what type of relationship exists between X and Y in this case, and in this case, and in this case. And I also ask you that how would you measure something like that, the relationship between X and Y mathematically? These types of questions are answered by covariance and correlation. This is a topic of covariance and correlation. So suppose you have following data, X and Y. Your X could be anything. It could be, let's say, study hours, and your Y could be score. And I plot them over here. So the first one is if a student studies for, let's say, 1 hour, his score is 20. So this would be this point right here. If a student studied for 2 hours, he scored 30. That would be this point. And if he studied for 3 hours, he scored a 50, 4, 40, and 5, 60. So I plot all these points over here, right here. These are my x-axis for study hours, and these are my scores. Now, by looking at these points, you can actually say that as your x is increasing, your y is also increasing. In this case, we can say that x and y are positively correlated. So now let's take a look at this one. In this case, I have x and y. Again, assume that your x could be the number of hours someone played video games, and your y could be the score in their exam. So this student, he played video game for 1 hour, and his score is 60. So I plot them right here. So this is my x-axis, and this is my y right here. This guy, he played video game for 2 hours. His score is 40. That would be this, and then 3, 50, 4, 30, and 5, 20. And these are my corresponding points right here. And you can see that as your x is increasing, your y value is going down. Your y is decreasing. In this case, we say that x and y are negatively correlated. Now let's take a look at this one. Here my x and y, I'm plotting them over here. So my x is 1, my y is 60, that would be this value. My x is 2, y is 20, that would be this. And then the third is right here, and the fourth and the fifth value. And you can see that as your x is increasing, your y has no specific pattern. Sometimes it goes up, sometimes it goes down. So in this particular case, you can say, just by looking at this visually, that x and y are not correlated. So in statistics, we use covariance to determine the direction of relationship between x and y. And this is the formula for covariance. Now, if your covariance is positive, it means that x and y, they move in the same direction. If your covariance is negative, that means x and y, they move in the opposite direction. And if your covariance is 0 or almost 0, then x and y are said to be independent. A side note, here I'm dealing with covariance of a samples. So anytime when you deal with samples, you use n-1 right here. But if you're dealing with population, then this n-1 will change to n. Now let's find the covariance between x and y, and for this data right here, this is given to you. So I'll be using this formula. So first you want to do is find your mean value. So my mean value for x would be, you take every single numbers over here, 1 plus 2 plus 3 plus 4 plus 5, and you divide by the total count, and your answer will come out to be 3. Same thing with your y. Calculate your mean value for y. You take 20, 30, 40, 50, 40, 60, add them all together, and divide by 5, and the answer is 40. And then you just substitute these numbers inside your covariance formula. So I'm expanding my covariance. This was the expression when I'm expanding that. In this case, my number of a sample would be 5. Put your n in this case is 5, so 1 over 5 minus 1. So the first one is going to be x1 minus x, so this is my x1. Okay, so x1 minus x bar, in this case 1 minus 3, because my mean value is 3, multiply by y1 minus y bar, which is mean value, so this is going to be my y1. So in this case, it's going to be 20 minus 40, because 40 is my mean value, plus, then you take the second one, you do the same thing, x2 minus x bar times y2 minus y bar. So in this case, this is my x2, and this is my y2. So substituting a value, 2 minus 3 times 30 minus 40, and then you do the same thing for x3. and then this is your y3, and you just substitute the numbers in there, and your answer will come out to be something like this: 40 plus 10 plus 0 plus 0 plus 40. Solving this expression, the answer comes out to be 22.5. So the covariance between x and y is plus 22.5. Now let's take a look at this example. In this case, I'm taking the same data as the previous one, except now I'm dividing my y by 10. So previously my y was 20, now it's 2, it was 30, now it's 3 and 5 and 4 and 6. So I've just taken out all the 10. So in this case, let's calculate our covariance. I'm using this formula again. My x mean was going to be same because your x has not changed. On the other hand, your y mean is going to be changed because now it has been scaled down. So you add all the numbers, you divide by 5, and the answer is 4. Apply your covariance formulas same way as I did before, and just substitute your values. So your x1 minus x bar, so this is my x1 right here, and this is my y1. So in this case, x1 minus x mean is 1 minus 3, y1 minus y mean is 2 minus 4. Okay, then do the next thing, which is right here, x2, this is my x2 right here, and this is my y2. So x2 is 2 minus 3, and y2 minus y mean would be 3 minus 4, and you can keep going like that. And if you solve this and you simplify this expression, your answer will come out to be 2.25. So your covariance is smaller by a factor of 10. So now let's plot these two examples we just did below. So this is my first one, and this is my second one. Let's say in the first one, the x was given to you in meters. And let's say the y is given to you in kilograms. So your covariance that came out to be 22.5, that would be 22.5 meters kilogram. Likewise, in the second one, let's say your x is given to you in hours, and let's say y is a score. So in this case, your covariance that if you recall, we just did calculation, came out to be 2.25, and the unit is going to be hours scores. So numerically, they look different. You can see that this is 22.5 and this is 2.25. So numerically, they're different, 2.25. But if you look at the visual right here, you can see they're identical. You see that this is identical. Look at that. So is there a way where although your covariance value is different for two different sets of data set, but you just saw that the shape of the curve is almost identical. The set of data points, they look almost identical. So is there a way where we can capture the strength of the relationship between two variables? And the answer is yes. We use something called correlation. And the way we find correlation, you divide your covariance by the standard deviation of x and the standard deviation of y. And this will give you your correlation. This is the formula for your covariance. In this case, my Sx is the standard deviation of the sample x, and Sy is the standard deviation of the sample y. On a side note, in this case, I'm dealing with sample. In case if you're dealing with population, then you replace your n minus 1 by n. So wherever you see n minus 1, like this right here, you're going to be using n over here. And another notation they use, they don't use Sx in that case for population. They use sigma x and sigma y. So we use correlation over covariance because it's a standardized measure and they're easy to interpret and compare across different data sets. So for example, if your data set 1, which was right here, this is given to you in meters and kilogram, and this data set could be given to you in hours and score. Now you can compare these two relationships using correlation. So let's understand this through an example. So before I give an example, I just want to explain a few key properties of your correlation. Number one, it is unitless. In other words, it has no unit. So your covariance, it's going to have some unit. Let's say your x is in let's say meters, and let's say your x is in kilograms. So your covariance is going to be meters, kilogram. And your standard deviation, on the other hand, right here, is in meters, and your SY, that will be in kilogram. So they will cancel each other out, and this way you will have no unit for your correlation. And the correlation, it always ranges from -1 to +1. If it's -1 or if it's near -1, that would indicate a very strong negative linear relationship. On the other hand, if it's closer to +1 or +1, that would indicate a strong positive linear relationship. If your value is near 0 or 0, that would mean your x and y has no relationship. Now, if the value of x and or y are converted to a different scale, then the value of r is not going to change. If you recall a minute ago, when we did those two examples, one of the y value was actually scaled by factor of 10 and your covariance changed. But this will not happen in the case of correlation. I will show you this in the next two examples. So in this example, let's say you're given a task to find the correlation between these variables, x and y. So I'm going to use this formula right here. So we have actually found our correlation already. Correlation between x and y was 22.5. We just did a minute ago. And then I'm going to find my standard deviation for my Sx and Sy. So standard deviation for x is going to be using this formula will come out to be 1.58. Same thing with your standard deviation for y, it will come out to be 15.8. Substituting these values in there. So in this case, it's going to be 22.5. That's your numerator. Your denominator is going to be 1.58 multiplied by 15.8, and the answer is 0.9. And this is the diagram for this. You can see the image. You can see the how this x, when it increases, then your y is also increasing. So you can see there is a very strong linear relationship between x and y. Now this is the same problem as before, except now my y has been scaled down by a factor of 10. So these are my new values of y. And now you have to find the correlation. So using the same formula, this is my Sx and this is my Sy. From the previous example that we did a minute ago, our covariance came out to be 2.25. You can calculate the standard deviation. It will come out to be 1.58, and the standard deviation for phi will also be come out to be same. I'm assuming you know how to calculate standard deviation by now. So substituting this value in the R, your answer is 0.9. So you can see in this case, the correlation has not changed. The correlation is exactly same. In other words, your correlation is not affected by scaling. Previous example, your y was 20, 30, 50, 40, 60, and I divided each number by 10, and now it's 2, 3, 5, 4, 6, and your correlation is still the same. So, although your covariance is different. For this one, it's 22 to 22.5, and for this one, it is 2.25. But your correlation, your R, is same for both of them. This is 0.9, and for your R in this case is 0.9. And you can see the shape of this line right here. You can see how this shape is exactly same as this shape right here. So your correlation is capturing the strength of linear relationship between two variables very effectively. Now back to this question. So which of the following has a strong linear relationship between x and y? And how would you measure that? Well, we are going to use correlation. We will find the correlation, and that would tell you how strong the linear relationship is between two variables. So in this case, this is my first data right here, x and y. And these are the corresponding values, and I even plot them right here. And I found your R came out to be plus 0.65 for this data right here. These are the corresponding values, and I plot them over here, and you can see that your you can actually calculate numerically, and your R will come out to be 0.85. And you can see that like over here and over here, that over here is kind of like a little bit there is a linear relationship, but not as strong. But this one is a little bit more stronger. And let's take a look at this one. In this case, this is my x and y, and I calculate my R, and look at that. It came out to be exactly plus 1. And you can see that everything is lying in one straight line. All the points are lying in one straight line. So anytime when your R is equal to plus 1 or very close to plus 1, your points are going to be lying on a straight line. Over here, you can see if this is your straight line, the points are not exactly lying on the straight line. And over here, you can see that the points are distributed around the straight line a lot more over here, less over here, and least over here. Now let's take a look at an example where your R is negative. In other words, you have a strong negative correlationship. So this is my data. I plot them over here and I calculate the value of R. It came out to be minus 0.9. So the line would be something like this, and you can see that your points are very close to this line, and they are, as your X is increasing, your Y is decreasing. Now let's take a look at this one. In this case, you can see that your x and y have pretty much no relationship. So I'm plotting these values over here, And you can see that as your x is increasing, your y actually sometimes it goes up, sometimes it goes down. It doesn't have any specific pattern. In this case, your r, I calculated, came out to be minus 0.07, which is almost closer to 0. In this particular instance right here, you can see that as your x is increasing, your y, on the other hand, is not changing at all. Your y is over here, 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 here. So in this case, your r is going to be exactly equal to 0 because there is no change in your y. So to recap, your covariance, if it's positive, it tells you that x and y are moving in the same direction. If it's negative, it tells you that they are moving in the opposite direction. If your covariance is 0 or close to 0, it tells you x and y are independent. And the major flaw of your covariance is this: it does not tell you the strength of linear relationship. All it tells you is the direction. That's why we need correlation. Correlation ranges from -1 to +1, and this is a little pictorial diagram to help you understand. Now, the value of R, which is your correlation, is very sensitive to outliers, and this can change dramatically if they are present in your data. So let's take a look at this example. Here, my x and y are given to me, and I plot these values. So you can see that it is a linear relationship, perfect linear relationship. Your R came out to be +1. I calculate the value of R is +1. Now here I injected an outlier right here. If x is 2.5, your y is 80. That would be this point right here. Because of the presence of this one outlier, your R changed from +1 to 0.53. So it changed dramatically. Now, I'm going to explain you about covariance and correlation matrix. So far we were dealing with only two variables. What if you have more than one variable? Let's say you have x1, x2, x3. You have many variables, okay? So for that, you can use covariance matrix. Each one of them tells you, each element as a matter of fact, it tells you the relationship, the covariance relationship between two variables. So in this case, let's focus on this one. This is telling you the covariance between x2 and x1. Um, by the way, you can also calculate the correlation matrix, which is similar. All you're doing is you're taking every element over here and you're dividing by your standard deviation. That's all. This is going to give you your correlation matrix. So you can find covariance and correlation matrix using some of the scripted language. Here I'm using pandas, which is part of your Python library. So in this case, I have four variables. This is my x1, x2, x3, x4, and I'm putting this in my data frame. Then I'm calling this dot curve, which is a short for covariance, and I'm also calling my correlation function, inbuilt functions. And it prints out my covariance and it prints out my correlation. So let's understand some of these numbers. Let's look at this one right here, 0.90. This is telling me that the correlation between the variable x1 and x2, that would be this one, your x1 and x2, is 0.90. In other words, it's a very strongly positively correlated. This one right here is a correlation between x1 and x3, and is telling me that is very strongly negatively correlated. This one right here is a correlation between x1 and x4, and it's telling me that it's almost equal to 0. This is closer to 0. So yeah, this is almost no correlation between x1 and x4. Your diagonal elements, by the way, this is one of the characteristics of your correlation matrix, is always going to be equal to 1. Well, that makes sense because if you look at the diagonal elements, let's look at this one right here. This is a correlation between x3 and x3. This is telling me that your x3 goes up, your x3 is also going to go up. So that makes sense. So your diagonal, that's why, is always going to be 1, because this is a correlation between between two same variables. And another interesting thing about these matrices, let me just remove everything. Another interesting thing about these matrices is that these elements, let me just draw a little diagonal line. So this element right here is same as these elements right here. Okay, so that makes sense too, again, because if you think about it, this one right here is 0.90. This is a relation between x1 and x2, and this 0.90 is a relation between x2 and x1. So that's why they will always be same. Now you can also see this relationship visually using heat map. So I have the same variables x1, x2, x3, x4, and I'm calling my heat map right here. So in this case, one of the characteristic of heat map is that your diagonal elements will always be equal to 1, as I explained before, and you will have a color map right here. This color map is telling you that anything that's closer to 1 would be red, and anything that's closer over here to minus 0.75 or minus 1 would be almost blue. So just by looking at the color, you can tell which variables are positively correlated and which variables are negatively correlated. In this case, all the red ones would be positively correlated. So you can see the red ones are like this one is red, and this is kind of like a little bit red, but not a lot of red. Okay, and let's look at the negatively correlated. Well, you have this right here, minus 0.9, because this is more towards bluish area, and then minus 0.7 again, this is more towards bluish area. And then you have the variables that are almost no correlation. In this case, you're going to have this color. Just by looking at this color, you can see that this one has like no correlation. And some of them basically are, rest of them, I mean, they are intermediate. Again, you can see that if I just draw a line like this, that these elements right here are symmetrically copy of these elements right here.